All right, we're back. We're on page 183. That last video took way too long. I should have broken it into like 3 videos. So I'm going to try to do better this time. We'll see. So what we want to do is parameterize each of these when we get to make our own choices. So what I'm going to do here, I've already set something up for us to look at. The most obvious choice that you can make when you actually have y as a function of x, or if you have x as a function of y, is to let the independent variable just be t. And just kind of go with it. So what I'm going to do is I'm going to choose x is t, then y is going to be 2t plus 3. And then because of that, we can see like t can be an element of the reals, which means x can be an element of the reals, which means we get the entire graph. And as t increases, x increases, which means that the orientation is we're increasing from left to right. So this will give us the whole graph. What I want to do for choice number 2 is a little different. I'm going to say 10 minus t. And then if x is equal to 10 minus t, then y is going to be 2 times 10 minus t, and then plus 3. Now t could still be any real value that you want, but as t increases, x decreases, right? Because if t is 0, we get 10. If t is 1, we get 9. If t is 2, we get 8. And so on. So as t increases, x decreases, which means you're actually moving to the left. Now, what I want to do is take a look at this. I set it up in GeoGebra ahead of time because it's kind of annoying. So I put in a spreadsheet, and I did some spreadsheet stuff. It's a little harder to see. Like if you press enter, you can see what I entered there. So but you can only see part of it. It's x of a of 8. And this is x of a of 9, or a9, and so on. So kind of a weird setup. But the idea here is when t is 0 for the first curve, which is just using v and then 2v plus 3. When t is 0, you're at the point 0.03, then you're at 1.5, 2.7, and so on. And then for the second curve, I use 10 minus v, and then 2 times the quantity 10 minus v plus 3. So this is the line segment. But this is the line, but only between t equals 0 and t equals 10. So you can see that if you look at the bottom of this row, you get 0, 3. The top of this is 0, 3. 1, 5, 1, 5. 2, 7, 2, 7. So what I've done is I've written equations that are going toward each other. They're going to collide at some point. So what I'll do is I'll just press play, and you can see that they're actually going toward each other. They're on the same line segment, going toward each other. There's a point at which they crash. It'd be interesting to know what that is. Like when are their x coordinates the same, or when are their y coordinates are the same. Now it's just going to bounce back and go the other way. So the parameterization that I've chosen here had a huge impact on which direction I was going, but they're going the same speed. So if t increases by 1, the x coordinate either increases or decreases by 1, depending on which way it's going, but it's only by 1. It's not like by 2. We can vary that up. Maybe here I'll just make this 2v, and then I have to make this 2v because I'm always doing the substitution. So now it's just going to go faster. So my table is no longer, my table is still accurate because it updates automatically. That's kind of interesting. This, for some reason, decided to change itself, and that's not fun. So now one of them goes a lot farther. So let's go back to 0 and see what happens. So you can see, maybe you can see A is moving faster. It's not really obvious. But in the same amount of time, A is going to go twice as far as it was previously going, or twice as far as B is going. So these are the choices that you have to make. You can basically choose anything, but it has an impact on the way the graph works, in particular the orientation, things like that. So let's see if I can get back to the notes. This next one, so we have x squared plus y squared. So that's a circle, but the radius is 3, which means I can only go like 3 in either direction from the center. If I can only go 3 in either direction from the center, I need to choose things that have an amplitude of 3. So what I'm going to do is I'm going to say, let's just take the unit circle and scale it up, right? The unit circle has a radius of 1, so it's 1 cosine, 1 sine. I'm going to make this 3 cosine and 3 sine. And I know what that does. So this is r equals 3, and that's where these 3's are coming from. So this, if I were to draw it, draw it terribly. We're going to start here at t equals 0, and we're going counterclockwise because it's basically the unit circle. I don't know, change it up to whatever you want. So I'm going to make this -3 sine, and I'll make this +3 cosine. All right, so I know I'm going to end up with a circle. And this is a great place to just like jump into GeoGebra, do it, play around with it, confirm that you're getting what you think you're going to get. We know we're going to get a circle. When t is equal to 0, the sine of 0 is 0. The cosine of 0 is 1. So I'm going to be at -3 times 0 is 0. 3 times 1 is 3. So I'm going to be at 0, 3. This is where you are when t equals 0. Now, the x coordinate, so the y coordinate has to decrease. It's not going to help us out. The x coordinate, on the other hand, could increase or decrease because you're starting in the middle. So you could go this way, you could go this way. The question is, which do you go? Since it's negative sign, you decrease, which means you go this way. So we're going here, there, and that's going to be our orientation. And I don't know why those dots show up sometimes. And you know, you could vary it up. You can do whatever you want. Pluses, minuses, sines, cosines, you can switch them. It's still going to work out for you. This next one here. Okay, so let's think about what happened for a circle, right? Circle, we're able to say, we know that we have x squared plus y squared equals r squared. And we use the trig identity, sine squared or cosine squared plus cosine squared. You know, you can like reverse those, equals 1. So we're able to use that. Well, now we need something that has a squared term, a minus, and a squared term. What are our other Pythagorean identities? So we could use, how do I have these memorized? 1 plus tan squared is equal to secant squared, which means that secant squared minus tan squared equals 1. And now it's like that game, I associate this with like pediatricians' offices for some reason, where it's like you have a square hole and a triangle hole and like a star or something. So you just match up the parts that fit. So like, look at this. We have a squared thing minus a squared thing equals 1. Squared thing minus a squared thing equals 1. Why not do it, right? So x squared over 36 minus 1dy minus 4 squared over 16 equals 1. All right. So if we associate them, then this will probably equal this, and this will probably equal this, and then they'll equal 1. So I'm going to say that secant could be just x over 6. I'm going to say that y, not y, I'm going to say tangent, get tangent could just be y minus 4 over 4. So that means that x could be 6 secant of t, and y could, so y would be first multiply by 4, then add 4. So 4 plus 4. I've been meaning to change that for years because it's like a little unclear which is which. So I'm going to go x is 6 secant of t, and then 4 plus 4 tangent of t. Well, do we know another thing that we could use? We do. We know that 1 plus cotan squared equals cosecant squared, which means that cosecant squared minus cotan squared also equals 1. Okay, so if that's true, we can do the same sort of comparisons. So we can say that that equals that, and that that equals that. And from there, we know that, I mean, it's the same basic math, so you end up with x would be 6 cosecant of t, and y would be 4 plus 4 cotan of t. It's like we just swapped out cofunctions. How weird is that? And can we just generally do that? I think we can, because like, here's like sine, this is cosine and sine, but we could just make this sine and this cosine. Like, why not? So it looks like maybe when you're parameterizing these, you can just switch out or swap out your cofunctions. All right. And then here, this is definitely the last thing we'll do. Maybe. No, definitely, because we're not going to have a 30-minute video again. You know what? I'm just going to stop this one here. I'll be back and I'll do that one in the next video. So I'm going to stop this here.